And it's time that we say to you that you should dedicate going to trying to communicate with your advisor of your major, so engineering, bio, computer science. I'll be meeting with the 40 some math majors on this campus. Um, Also, I would say, especially if you're a sophomore, I don't think many of you are, you could start looking at the process for graduation because it's a pain in the ass, how much you have to do, all of the checklists and everything. You should also start looking at tomorrow, dedicate some time to spring semester. The schedule's out, so you can see when the Calc 1 classes are going to be, right? You can start to plan out your schedule. I think registration should happen in 2 more weeks, okay? But I'll keep you notified on that. And then the other thing is use the day to catch up. Yeah. But I'm home. I'm going to be Zooming with my math majors, but you can certainly send me emails anytime. And when you send me an email, it should have the picture of the problem, a picture of your work, and then maybe some kind of comment. Not sure why I'm not getting the solution here. Having trouble with Desmos here. You can give me a picture of what you have in Desmos too, right? And most of the time, I'll say, "Oh, you just missed a negative," right? Or, "Okay, you didn't factor correctly," and I'll jot down the correct factoring, and so you can keep moving. So I'm willing to do that all the time, any day. Most of my students are sending me emails at 2 or 3 in the morning. I'm not going to respond then, but if it's old man time, I can respond. So 6 in the morning until 4 in the afternoon, I'll respond right away. But yeah, so that advising day is, I don't know if it's as valuable if you're 3 semesters away from transferring, but it's pretty valuable if you're 1 or 2 semesters away. But it's a lot of work, and for me, I'm ADD, so when I try to do my graduation application, oh my God, it took me forever. Yeah, Jason, here's your test. I'll leave some time at the end if you have questions. Solutions are on Blackboard, okay? So I want to help. I'll do anything I can to help. I would love to see you in my calc class next semester. I'm teaching 2 of them, but if you can't do this stuff, I'm telling you, it's just going to be more difficult, right? And once all the names are on the Calc 1 list, I'll say to you, I'll let you know, hey, this person is a lot nicer than I am. This person doesn't grade as tough as I do, right? This person is available a lot, so you want to try and figure out your schedule. For me, for my schedule, it was I cooked in a restaurant for lunch from like 11 to 2, and then I taught guitar students, mostly high schoolers, from like 3 o'clock until 6 o'clock, right? And then so I could take a class early in the morning or after in the evening. So my schedule was not based on teacher; it was based on when I was not working. So if you're in that situation, you don't have a choice. You're going to take the classes when you can take them. But if you have a choice, why not do a little research, right? So anyway, 4.4, we're talking about rational functions. We're talking about graphs of rational functions, and we're talking about sign tables with rational functions. So in my opinion, it's one lesson, but the problems from 4.4 to 4.5 to 4.6 build up. And of course, like for me, I see maybe 1 or 2 questions from this whole group, right? So So let's see how it goes and see what we do, okay? All right, here we go. So we're talking about 4.4 properties of rational expressions. Sorry, rational functions. So first of all, a rational function is a p of x over q of x, where p of x and q of x are what kind of functions? The numerator should give you the hint, p of x. Polynomials. Right, so I don't want to see square roots or, exponentials, that type of thing, right? And then what's important about the downstairs function, q of x should never equal what? What? 0. So we got to look at a couple of things, but let's look at the mother function of rational functions, right? So the mother that we're really talking about is y equals 1 over x, or y equals 1 over x squared. And we're gonna use our knowledge of those things to talk about what I call short run behavior. So 1 over x looks like this, and 1 over x squared takes all my negatives and makes them positive, right? So this one really looks like, in general, 1 over x to the odd power, x to the 1, x to the 3, x to the 5, and this one looks like 1 over x to the even power. And it's kind of nice to do this on Desmos, and I'll invite you to do it right now, right? So going to Desmos. And if I do y equals 1 divided by x raised to the odd, which is a 2n minus 1, oops, sorry. So, oh no, I still have it wrong, sorry. Let me just do it this way. Let me just make it an n. And let me change my scaling by ones. So I'm going from 0 to 1 to 2 to 3 to 4, or 0 to negative 1 to negative 2 to negative 3 to negative, right? No, I don't want to go less than 0, less than 1. Okay, that's it. So when it's odd, you see that shape. When it's even, you see the symmetric there, right? So when the power is odd, it looks odd. The function's odd, right? You see the symmetry about the origin, right? And then when it's even, I've got symmetry around right this way, reflecting this way. And if I keep going, 1 over x cubed, it looks like 1 over x again. And 1 over x to the 4th looks like 1 over x squared again, right? They're not really changing. When the power's odd, it looks like 1 over x. When the power's even, it looks like 1 over x squared, right? There is something that's happening. Do you see anything that's happening? If I just go to x to the 6th and then 8th, do you see anything that's happening? Yeah, it's the base is getting closer to the axis, and the height is getting steeper, right? So kind of nice to really look at that like this. So 1 over x, 1 over x cubed, 1 over x to the 5th, right? So I'm kind of asking you to explore a little bit. So you see the darker function is getting steeper and closer to the, right, the axis. Helps if I zoom a little bit, right? You see the 3 colors? Look at, so on the right-hand side, blue, purple's pushing down, black's pushing down. But look at the blue going up and then the purple going up and the black going up, so you can see the steepness, right? Or the depth as the powers keep going. So we want to think about these two mother functions as we're starting to deal with rational functions. Okay? Nice. Let's make this our first rational function. Go ahead. Yeah. Yep, absolutely. Right, so just talking about rational functions, and then my first thought is, well, what are some mother functions of rational functions, right? Yeah, you got it. So let's look at our first rational function here. Let's call it f of x, right? And let's do something nice and simple like x minus 1 over x plus 3. So can you think about what I would want to know about this function? Well, what it looks like, for sure, right? And so how are we doing that at this point in our math careers as Desmos or calculator, right? So I want to go right away to my function and take a look at it. Every time I give you one, if you don't know what it looks like, graph it. If you do know what it looks like, graph it anyway, just in case you're wrong, right? Was it x minus 1 all over x plus 3? So what else do you think? I thought I had wrote x plus, let me just double check, x plus 3, x minus 1 over x plus 3. So points, we want to know points, right? Like what? What kind of points? Nice, x or y intercepts, right? It's not a bad idea to put a couple of other points on there when you're graphing, even blindly, right? So I'll show you what I mean. If I use Desmos, if I use my f of x notation, I can put something like f of, I can pick a point in the domain, like 1, and then plot f of 1. And so you can use Desmos pretty strong just to plot a bunch of points, right? And of course you could verify this, what happens when I plug in 1 into this function. I get 1 minus 1 over 1 plus 3, right? I get 0 over 4, which is 0. So you should be able to plot any point you want. We're typically trying to find nice points, points that end up on the crosshairs, I call them vampire points, right, where the axes cross. So let me change my axis here to 1, step by 1. Right, so you can see a nice point there at 1, 0, right? You with me there? So we want to be able to plot points. And I'm going to bring that back into play when we do sign tables, because I kind of like to be able to plot a point between my critical values, right? I'd like to be able to plot a point between left of, right of, and my critical values, right? Good. What else should I know about this function? Just looking at the graph, what should I know? The domain, right? What x values am I allowed to plug in, right? So in all of our rational functions, we're going to have this one rule for domain. You can't divide by 0. We're not going to have square roots, right, because they're not polynomials. So you cannot divide by 0, right? So do not divide by 0. So that means set the denominator equal to 0, right? And in this particular case, x plus 3 equals 0 gives me x equals -3, right? And so when the denominator is 0 and the numerator is not, we have something called a vertical asymptote, a VA. A vertical asymptote. That's 2 words. So vertical asymptote, when the denominator is 0, but the numerator is not. So P of x over Q of x, right? And Q of x is, go ahead, say it to me. So I like you to graph your vertical asymptotes with a dashed line. So I'm going x equals -3. I'm going into my gearbox, right? Don't let me go too fast here. Sorry, x equals -3 into the gearbox, and I'm going to label that line with a dashed, right? Something like that's fine. Maybe a lighter color so I'm not confusing the actual function with the asymptote, right? Functions will never cross a vertical asymptote. Why? I'll go back in a second. Why? Say it again. So if it crosses, there's got to be a point there, right? If it crosses that vertical asymptote, the function's got to be a point there. But that point is what's making the downstairs 0, and not until next semester will you know how to divide by 0. Okay? Right now we've been saying what? Divided by 0 is what? Undefined. What the hell does undefined mean? It means that the slope at that point, the line is vertical at that point, right? And so, but the problem is we don't know if it's a positive infinity or a negative infinity. We can't tell, so we call it undefined because it's both of them. But the key is I can't plug in that number to the function; it just doesn't exist. So there can never be a point there. Eli, I don't know if that's what you said, but I'm getting new hearing aids this week. Someone asked me, what kind? I said, what kind is it? And I said, oh, it's 240. So we have vertical asymptotes, right, when the denominator is 0. What happens? So we have what's called an removable discontinuity. This is a calculus topic, but I see no reason not to teach it to you now. Removable discontinuity, let's say a is a real number, and I've got my function, which is a p of x over q of x. And f of a equals 0 over 0, meaning p of a equals q of a equals 0, right? My numerator and my denominator are 0. Question? I went a little crazy with my cursive. I was a really good student in like middle school when we had to learn cursive. I don't know, did you all remember this? You remember this? I was really good at cursive. Get it? Cursive. A belongs to real numbers. Yeah, it's a belongs to. Yeah, I was really good at cursive. I got, of course, kicked out of Catholic school, but so a removable discontinuity is kind of weird, and we want to think of standard form. So f of x is just so both p of x and q of x are in standard form, right? Does that make sense? So I might have something like this. And then I want to think of factored form. Right? So my numerator would be some ax plus b, or cx plus d over 2x minus 1. So I want everything factored, right? Does that make sense, what I'm saying? I want my numerator completely factored, my denominator completely factored, if possible, okay? So let me show you an example of a removable discontinuity. Yeah, say again? Yep. You can say, slow down, buddy. So standard form is just a polynomial, right? Factored form, it's a polynomial, but factored, right? Upstairs and downstairs, right? Make sense? So I'm going to spend another 10, 15 minutes going through theory, and then we're going to just do a whole bunch of problems, okay? So again, everything I'm putting here is going to go on your formula sheet, right? All right, let me give you a classic problem here. Sorry, let me go to a new page. Chris, you okay? And remember, you're all paying me, so don't let me go too fast. If you need to go back, I'll go back. I'm not in a rush, okay? So just going to look at a classic here, x squared minus 4 over x minus 2. So that's standard form, right? Yes, you with me? Anybody see how that upstairs factors? It's x plus 2 times x minus 2. Right? This is factored form. Yes, you with me? And then if you notice that I can cancel those two out, they're the same factor, they cancel out. This is what I would call reduced form. You won't always get a reduced form. You won't always get a factored form. Okay? You'll always get a standard form. I try and make sure you get things that factor so that you can factor for sure, practice factoring, and things that reduce so that you can notice that you'll have pieces that cancel with each other, right? So the key here is in all of these, the domain is the same. What's the domain in the first function? X is not what? Yeah. And so that's the same in all of them. Just because I canceled a factor out doesn't mean it's now I can put a 2 in. I should still get something over 0. And the key is here, I get 0 over 0, right? Do you agree with that? F of 2 is 2 squared minus 4 over 2 minus 2. So that's 4 minus 4 over 0. That's 0 over 0. Now, I like the question mark there because I don't know what it is. It's indeterminate. How are we doing here so far? Are we okay? This is not difficult, right? It's just a lot, right? Do you agree with me? Nothing we're doing is difficult, but it's overwhelming. It's a lot to think about. It's a lot to remember. And I'm saying to you, well, I'm a human. I'm not a sadist or a masochist. I don't want to torture students. So I'm giving you a formula sheet, but you've got to you've got to still get some understanding from what you see to what you put on that paper, right? And it takes time. It's like if you're a musician, the first time you learn a major scale, do, re, mi, fa, sol, la, ti, do, boring as all heck. But you have to learn it that way first, and then you can start to improvise. Same way, when you learn how to shoot a basketball, how the ball rolls off to your fingertips, right, with a little backspin. You got to learn that piece first before you start playing like Julius Erving, which is he's one of my heroes, or George Irvin, the Iceman, finger roll. You know any of these people? This is the 80s, so. But until you can get the basic thing down, you can't improvise, right? So look at what happens when I graph this function. It's pretty interesting. Right? So f of x is equal to x squared minus 4 all divided by x minus 2. Oh my God, what does it look like? It looks like my reduced form. It looks like a line, y equals mx plus b, y equals x plus 2, right? Is there a vertical asymptote? So there's a spot where the downstairs equals 0, but the upstairs also equals 0. So no vertical asymptote. So what's happening at f of 2? And notice I put that into reduced form, is I should see the height of 4, right? So meaning I'm going, okay, when I put in a 2, I should see a height of 4, but I know with the gearbox that that point doesn't exist, so there's really a hole there. Do you see 2, 4 now? So I've got two things already. I've got a vertical asymptote. That's when the downstairs is 0 and the numerator is not. I've got a removable discontinuity or a hole, I'll say a hole, when the numerator is 0 and the denominator is 0. I've got an x-intercept and a y-intercept there, right? So this is everything we've talked about so far. Yeah, we okay? I've got my standard form, my factored form, and my reduced form, all with the same domain. How are we doing? It's not difficult, but everything together is difficult. Like walking to California is difficult, but every step is simple. Hopefully you don't start walking toward Florida first, but you know, every single step is easy, but the whole thing is not easy. Right? So you have to practice each step, and you have to practice the overall. What am I supposed to know about these functions? Why is going to come a little bit later. Why do I have to know this? Because I'm trying to make calculus easier. All right, so what do I have so far? Intercepts or arbitrary points. Yes. Yes. It's really close to. I'm kind of cheating because I'm not allowed to plug 2 in. And you'll see me use this a lot in short-run behavior. Short-run behavior. And this is my thing. It's not, you won't see it in books, but I'm saying f of 2 really behaves like x plus 2, x minus 2 over x minus 2. These cancel, right? So it really behaves like x plus 2. It can't be equal because if I put it in, I get 0 over 0. But I'm trying to think about, well, what would the height be if I could put it in? So I'll use that approximation symbol. Because I can't do it. Yeah. All right, we got more. We need horizontal asymptotes. And this is fun for me because I get to, you ever see Dave Chappelle? So it's Dave Chappelle doing Rick James, right? So this is my horizontal asymptote little skit. If I'm talking about f of x equals x squared minus 4 over x minus 2, this thing in the long run behaves like, behave. X squared over x, which is equal to x. Wait a minute, did I have that right? Yes. So in the long run, this thing behaves like the mother function over the mother function. Right? Do you see what I did there? I got, instead of x squared minus 4, I got just x squared upstairs. And instead of x minus 2, I just got x downstairs. And it's me going, if x is $1 million, right? If x is $1 million, do I care about losing $4? Hell no. Probably to a fault, but that's, God bless America, right? If x is $1 million, oh, I'm sorry, I have x squared. I don't have 6 zeros. That's $1 million, right? I have 12 zeros. For x squared, that's 12 zeros. Imagine how much money that is, right? So do I care about the $4? Hell no. I'm rich, bitch. Right? That's the Dave Chappelle doing Rick James. I don't care about that extra pieces, right? Especially even here. I don't care about the losing $2. If I have $1 million, I'm probably blowing my nose in $100 bills, right? So I don't care about $2. So all I care about is the mother function in the long run. And so we would like to look at that vertical asymptote, if it exists, of y equals x. That's what I got, right, when I did mother function over mother function. And probably I want to look at that again as a dashed line or so. So in the long run, does my function look like this dashed line? Of course. It shifted a little bit, but who cares, right? So this is not really a horizontal asymptote. This one's called an oblique. So I'll have horizontal asymptotes. I'll have oblique asymptotes, which are like a y equals mx plus b. I'll have quadratic asymptotes, which look like an ax squared plus bx plus c. I could have cubic asymptotes, et cetera, et cetera. We try and restrict it to obliques. Okay? So let me give you a better example. So here's my function. I want several things, right? I want intercepts. I want vertical asymptotes. I want domain. If you can give me range, great. We're going to learn how to do range in the next chapter. I want horizontal asymptotes or oblique asymptotes. I want the holes, right? Those removable discontinuities. I want my standard form, got it. I want my factored form, who's got it? Nice, downstairs, right? Oh, you gave me the reduced form, right? Upstairs is x plus 2 times x minus 2, right? Downstairs is x minus 2, x minus 1. Yes, you with me? Yep. That's okay. Tell me. Yeah, how I got the factor form here? Yeah. So we learned, so going back to Algebra 2, and if you didn't do it, you want to just kind of do a search for this and put it on your formula sheet. How do you factor quadratics, right? So, so we want to be able to factor ax squared plus bx plus c. And we had a whole bunch of shortcuts. If we had an a squared minus b squared, we got a plus b times a minus b. And that's where I'm doing the numerator. X squared. So x squared is something squared. 4 is something squared. So I get x plus 2 and x minus 2 for my factors. Does that ring a bell at all? Yeah. And then when we have x squared plus bx plus c, we said f1 plus f2 equals b, and f1 times f2 equals c. So we got x plus f1 and x plus f2, sorry, minus, both of them minus. So this is how I'll say it as a human. What two integers multiply to 2 and add to negative 3? What two integers multiply to 2 and add to negative 3? Negative 2 and negative 1, right? Negative 2 times negative 1 is positive 2. Negative 2 minus a negative 1 is negative 3. You remember seeing that at all? Yes. And there's one more level higher, which is if I have ax squared plus bx plus c, now I need integers that multiply to ac and add to b. So a times c is f1 times f2, and f1 plus f2 is b. And I call this the AC method. So you'll see me do at least one of these today. But the whole theme is how do you factor quadratics? And remember, how do we factor things that are higher than quadratics? Synthetic division. We're going to take the function, take the quadratic, take the polynomial, graph it, see where it hits 0, and synthetic divide until we can chip it down to one of these quadratics. Yeah, yes. So look at this function that I have now, right? I can do my reduced form. Do you see it? The reduced form, the x minus 2's are going to go away, right? So my reduced form is now x plus 2 over x minus 1. Standard form, factored form, reduced form, right? What else do I need? Domain, what is it? One or two are bad, right? Right, I'm just looking what makes the denominator 0, yes? So the domain on all of these is the same. Even though the last one seems like it's okay for me to put 2 in. But we know when I put 2 in, what is actually there on the graph. Exactly. So the whole is going to happen at 2 comma what? Do you see it? 2, 4. No? I'm putting the 2 in my reduced form, and what do I get upstairs? I'm putting the 2 in here, right? So I get 2 plus 2 upstairs, that's 4, and a 2 minus 1 downstairs, that's a 1. 4 over 1 is 2. Sorry, 4 over 1 is 4. Right? Where are my vertical asymptotes at? So I don't have a vertical asymptote at 2 because the upstairs is also 0, right? But where do I have a vertical asymptote? Where do I have the downstairs equal to 0, but the upstairs not equal to 0? X equals what number? Yes. What's my horizontal asymptote, right? Horizontal asymptote is f of x is approximately equal to x squared over x squared, which is 1 in the long run. Right, in the long run. So remember, I'm looking at this function, but the top behaves really like x squared, and the downstairs behaves like x squared, right? Because I don't care about those other smaller pieces of money, right? Yep. Where? Yeah. So horizontal asymptote. I'm thinking of the mother function of the numerator over the mother function of the denominator, right? And I have to fix what I said about oblique asymptotes. I want to fix that, but I will soon. In the long run. So we'll talk about long run behavior, and we'll talk about short run behavior. So long run behavior is when x goes to infinity or plus or minus infinity, way out to the right and way out to the left of the function. Let's take a look at the graph right now, okay? And please do this with me as we go. So f of x is my original rational function. I had x squared minus 4 all divided by x squared minus 3x plus 2. I had a vertical asymptote where at x equals 1. And again, notice that the function is not crossing that. I had a horizontal asymptote at y equals also 1, right? A function can cross a horizontal asymptote in the short run, not in the long run. But a function can go across a horizontal in the short run, around the origin. How's that? Okay. In the long run, way out left and right. Short run by the origin, long run way outside. I had a hole in the function at what, 2, 4? Is that right? And it looks like I have an x and a y intercept, right? What are they? So how do I get my y-intercept? What do I let x be? Yeah, let x be 0, right? So I get f of 0 equals 0 squared minus 4 over 0 squared minus 3 times 0 plus 2. Oops, sorry, I made a mistake then. So that's negative 4 over 2, that's negative 2, sorry. Yes. There's two places the denominator is 0, and only one of them matches with something where the numerator is 0. If you looked at my factored form, right, you can see that when x is 2, those will cancel. So that's where my hole is. Exactly. When you get a 0 over 0, we call that indeterminate. It's one of the first things we look at in Calc 1. But, we're just trying to get you ready for it. So we're looking at where those things can cancel. So I'm almost pretending like it was never an issue. But, of course, it gave me a 0 downstairs, so it's an issue. How did I get my x-intercept? I look at my reduced form, right, and set the numerator equal to 0. So my x-intercept is -2, 0. Let me put that in. Nice, I like to see that, right? I see it right away, it hit the graph. And my y-intercept was 0, -2, right? So you're going to be doing homework and going, oh, I didn't put the intercept in, how do I find that again, et cetera, et cetera. You got to, right? You got to be building this formula sheet for yourself as you go and have it organized, right? If I have a rational function, these are all the things I should find, and how do I find them, right? I want to look at the short run here. How are we doing? We okay? Look at my short run. And that's going to happen when x is 1. Right? So I get x plus 2 over x minus 1. And I'm going to say to you that I could put the 1 in upstairs. I can put the 1 in upstairs because it doesn't get me in trouble. But I can't put it downstairs because it gets me in trouble. And when I put that 1 in upstairs, what do I get? You see it? 3 over x minus 1. So what's the mother function there? A 3 over x. Look at the shape of the curve at x equals 1. Do you see that same shape as 1 over x there? Do you see the same shape? Look at I said 3 over x, right? That's the mother function 1 over, right? It looks like 1 over x, yes? And look at that shape on my curve. Do you see the 1 over x shape? That's short run behavior. Not many books will talk about that. And you don't need it because you can cheat all of that using Desmos. That's the thing, is I'm really teaching you how to be a good American. I'm going to teach you how to cheat as much as possible and then put the work on the page to make you look like you're really intelligent. Right? I want you to use the geometry, use the graph to show you that your algebra is correct. If you take pre-cal or Calc 1 or Calc 2 at UMD, they don't allow calculators at all. It doesn't mean when you're off campus or outside of the classroom you're not practicing with the calculator. You still are. But when you go take a test, you've got to have all that knowledge in here, right, when you take the exam. Oh, you don't use anything when you get a job, no matter what job you do. But we're trying to do a couple of things. We're trying to see if you have the maturity, intellectual maturity to go to these really abstract concepts. And math is a really great way of checking that. Computer science students have a huge advantage. You could just hack into Russia and be famous and rich. You could make your own software to be famous and rich, or you can go through academia.